Okay, this is Leetcode 1642, the furthest building you can reach. Pretty simple problem description. You're just given an integer array that represents the heights of buildings, and your objective is to try to maximize how far you can get to the array by following the constraints. So you start at index 0, and you need to try to get to the next building. If you're ever at a building with a height that is greater than the height that comes after it, so the index that comes after it, you can get there without using any of your resources. So your resources are up here, bricks and ladders. But if you're ever at an index with a height that is less than the height that comes after it, so for instance this 4 is less than the 12, you're going to need to dive into your resources in order to get to the next building. And the resources work differently. The bricks, you can get to the next building by basically using the same amount of bricks that equals the difference between the two. So in this case, you would have to use 8 bricks to get to the next building. And the ladders work in a way that are kind of overpowered in this problem. You can use one ladder for theoretically an infinite difference between the two. So you would only need to use one ladder to get from 4 to 12. You would only need one ladder to get from 3 to 18, and etc. So ladders, as I said, are overpowered. Remember that because we will come back to that later in the problem. That property is important. So at this point, what the light bulb that went off in my head was the decision that you had to make. You have to make a decision between using bricks and ladders whenever you reach a building where you can't get to the next step without using some resources. So whenever I hear decision tree, I obviously think dynamic programming or memoization. And that intuition makes a lot of sense and it works in theory. However, it will get you time limit exceeded and you won't pass all the solutions on Leetcode. So the intuition behind that is pretty simple. You either use the 8 bricks to get to the next step or you use the 1 ladder. And that decision then determines what you would use for the next, what you would use for the next, etc., all the way down the tree. So the tree keeps going, and you would then return whichever index gets you the furthest along the array, which would end up being something like this. And whenever dynamic programming or memoization doesn't work, what we need to think is how can we be greedy with our solution? And like I said earlier, the ladders in this problem are overpowered. So why don't we try in each iteration, why don't we try to, whenever we encounter a building that we can't get to, why don't we try to use a ladder until the ladders run out? And if we go through this, we're going to need to use a ladder here. So the ladders go down to 1. Then we're going to not have to use anything here. We're going to need to use a ladder here. So ladders now go down to 0. Don't need to use anything here. Then at this point, the difference is 15. So the difference here was 5, the difference here was 8. The difference here is 15. We have no ladders left, and we have no bricks left. This is not, though, the optimal solution. So what we need to think is how can we store the differences in here where once we reach a point where we have a greater difference, we can easily switch the ladders. And the data structure that we're going to use to do that is we're going to use a heap. And all we're going to do with the heap is we are going to just store inside the heap the differences. So we're going to continue to just use the ladders, but we're going to store the differences between the two or between the different buildings. So we're going to store this difference. We're going to store the 8 in the heap. And then we're going to store the 5 in the heap. And whenever we then get to a point where our ladders is at 0 and we have a decision to make, we have a 15. So we have 15 as the difference here. We're going to compare this 15 to the 0th index in the heap. So the 0th index in the heap would be the 5, even though it is in this example. But the 5 would be the 0th index because it maintains the sorted property, and it's efficient log n insertions as well as log n deletion or pops, log n pops. So we would compare the 15 to the 5, and if the 15 is greater than the 5, what we're going to do is we're going to pop the 5, and we're going to push the 15 onto the heap. And we're not done at that point, because what we're doing is we're switching the ladder from using it to get from here to here to using it to get to here to here. So we need to make up that difference in the bricks. So what we're going to need to do then is we're going to have to subtract the bricks by 5. So then we go to the next problem here, or the next building here, and the difference is 2. 2 is not less than 8, so we need to dive into the bricks again. This then becomes 3, and we can obviously go to this next one, and then we end up reaching a point where we're going to have to do a couple more push-ins and pops, but we're not going to be able to get to the last, so we're going to end up returning this 7th index here. So we need to remember, whenever dynamic programming doesn't work, to try to use the greedy solution, and this solution is a one pass, so one pass O of n, but in order to use the heap property, we need to do log n pushes and pops from the heap. So the time complexity of this comes out to O of n log n, which is obviously a lot better than the exponential time complexity of dynamic programming. And here is the coding solution. Quite frankly, this is a lot easier than the memoization dynamic programming one, in my opinion. However, the intuition is not as straightforward. All we're going to do for this is we're going to initialize the heap to a dynamic array, and we are going to loop through, but because we are doing this in one pass. However, the one thing we're going to change from a standard loop is we are going to only go up to the second to last value in heights. And the reason we're doing that is because we're going to always be comparing the the value at the current index to the value that comes after it. And we want to avoid the index out of bounds error, but we also, when we're at the last building, we don't care about trying to compare it to the building that comes after it, because there's nowhere more we can go, and it'll raise an error. So we're just going to kill it at this point. And first, what we're going to do is we're going to compare the difference, and if the difference is ever less than or equal to 0, we know we can just continue. So all we're going to say is if the heights I plus 1 minus the heights of I, so the value that comes after it in the array, if this is ever less than or equal to 0, we know we can continue with the loop. Next, we're going to be greedy. So we're going to, if this one doesn't execute, we know we can be greedy, and we're going to say if the ladders is ever greater than 0, we know we can use the ladder. So we're going to use the ladder. And the next thing we're going to do is we are going to push whatever the difference is onto the heap. So we can say heap q.heap push onto the heap. This is obviously Python syntax, but can be used in other languages with the standard library. And we're going to push the difference to the heap. And the next thing we're going to do is we're going to, there's one edge case here that I wanted to just touch on briefly. The ladders can sometimes be 0. So theoretically, the heap could be empty in certain cases. So we always need to check in this spot if the heap contains values. So elif heap. And then what we need to account for is we need to check if the difference here, if the difference is ever greater than the smallest value in the heap and the smallest value in the heap is less than or equal to bricks. And the reason we need this last point is, so all we're doing here is we're checking if we can make this swap. So if we can make this swap, then what we're going to do is we're going to need to decrement the bricks by whatever the value of heap is. So we do not want, we need to know that we have enough bricks in order to make that, in order to use the bricks to get up to that next level. So all we're going to do is we're going to store a variable named value with heap q.heap_pop from the heap, and we are going to then push to the heap in the same way, and then we're going to decrement the bricks by the value. Now just a couple more conditionals here. We're going to then check if the bricks is greater than or equal to the difference, then we can decrement the bricks by the difference. And then the last else case, if none of these execute, we know that we can't get to the next building. So that means we can just return the current index. And the last thing to remember is if we ever do make it through the loop, that means we can return the length of heights -1. And this is the full code. And this should work unless I made some syntax error. There you go.